building on what we worked on in lecture number 1, we're now going to continue to talk about the electronic structure of the atom. What we'll do is review how to write electron configurations for cations and anions. Then after that, we'll talk about how to calculate the effective nuclear charge on an electron in an atom or an ion. Remember that from the first lecture that we looked at the Schrödinger equation, which gives us an idea about where electrons are in atomic orbitals. We came up with 4 quantum numbers: N, L, M sub L, and M sub S, that helps us write electron configurations. Electron configurations are a description of how the electrons are arranged in atomic orbitals in an atom or an ion. We can use the periodic table to map the distribution of electrons in these atomic orbitals. And this is based upon an idea known as the Aufbau principle, which means building up. You fill atomic orbitals with the lowest energies first. There are 3 basic rules for writing electron configurations. First is the Aufbau principle, which we just talked about. It's where orbitals are filled in order of increasing energy. So we start off by filling the 1s, then the 2s, then the 2p, then the 3s. So with more and more electrons, we add more subshells or more collections of orbitals for these electrons to reside in. The second rule is called Hund's rule. So when we have a set of orbitals that are degenerate, that means they all have the same energy, like say all 5 3D orbitals. Electrons cannot be paired up in a single orbital until every orbital contains 1 electron. Electrons in orbitals in a degenerate set must have parallel spins. For example, they should all be pointing spin up. The third rule is called the Pauli exclusion principle. No 2 electrons in the same atom can have the same values of N, L, and M sub L and M sub S. It follows that the minimum that 2 electrons can differ by is the M sub S value. Looking at the ordering of subshells in atoms, the one with the lowest energy is going to be the 1s orbital. As you get further and further away from the nucleus, the potential energy increases. So the 2s has the second lowest potential energy. The 3 2p orbitals have the third lowest potential energy. And it increases up to the 4s in order of SP, SP, S. Starting with the 4s, the next highest in energy is the 3d, then the 4p, and that continues through the entire periodic table. Now, when writing electron configurations, we can look at the periodic table to help us. So, for example, if I start right here, that's hydrogen's position. Hydrogen has 1 electron, so its electron configuration should be 1s1. Helium is the second atom on the periodic table. Therefore, it should have an electron configuration of 1s2. By the time you have an electron configuration of 1s2, the 1s orbital is completely filled. So now we must start filling the 2s. Lithium is the next atom up. So the electron configuration for lithium is 1s2, 2s1. The neighboring atom is beryllium. Beryllium has 4 electrons. So its electron configuration must be 1s2, 2s2. You can continue this throughout the periodic table. Let's take fluorine, for example, which is right there. It has 7 total electrons. So we must put 2 in the 1s, 1s2, 2 in the 2s, 2s2, and 5 in the 2p, 2p5. We can do this for atoms even more complicated than just fluorine. We could look at an atom like scandium, which resides right there. The electron configuration building up to scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Now, look at example 3. I want you to take some time and write the electron configuration for the following atoms: phosphorus, titanium, chromium, krypton, and praseodymium. The number in parentheses is the atomic number for those atoms. Here's the solution to example 3. Notice that phosphorus has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p3. Titanium has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Chromium has 2 possibilities, and that's what I'm showing here. Both of them have a certain set of orbitals that are filled the same. The 1s2, 2s2, 2p6, 3s2, 3p6 are the same for both electron configurations. In the first possibility, you've got 4s2, 3d4, or the second possibility is 4s1, 3d5. So my question to you was, which is correct? We're going to discuss which one is correct in 1 minute. Next is krypton, which has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. And finally, the fifth option, or the fifth question, asks you to write the electron configuration for praseodymium. Now, both electron configurations are the same up to 5p6. They both have the exact same electron configuration. The first possibility has an electron configuration of 6s2, 4f3, whereas the second possibility has an electron configuration of 6s2, 5d1, 4f2. So, which is correct?